Good day, this is Team Erbrium and we will be discussing the inorganic chemistry topic titled Into the Quantumverse, describing the electronic structure of atoms and how waves came into the picture. In our discussion, we'll have the following subtopics. I am Donica Suan and I will be the one to start this report by talking about the transition from classical physics to quantum theory. Particularly, I will explain the properties of waves, electromagnetic radiation, and Planck's quantum theory. Following that, I will also discuss Einstein's explanation of the photoelectric effect. Now we must first understand the nature of waves. First, waves can be defined as vibrating, physical disturbances by which energy is transmitted. They are characterized by their length, height, and by the number of waves that pass through a certain point in 1 second. To represent these attributes visually, we will use a wave profile diagram of water waves. The crest is the highest point of a wave, while the trough is the lowest point, and wave height is the vertical distance from crest to trough. The amplitude is the vertical distance from the midline of a wave to the peak or trough, while wavelength or lambda is the horizontal distance between identical points on successive waves, and the number of waves that pass through a particular point in 1 second is referred as frequency or nu. Since wavelength expresses the length of a wave, and frequency indicates the waves that passes through a certain point in 1 second, the product of these two terms results to another important property of a wave, which is speed. Now, aside from water waves or sound waves or light waves, we also have electromagnetic waves that are invisible light. This theory was proposed by James Clerk Maxwell, where he defined electromagnetic waves as waves with two components, an electric field component and a magnetic field component that have the same wavelength, frequency, and amplitude, but travels or oscillates in two mutually perpendicular planes. The speed of electromagnetic waves, or more commonly known as speed of light, or c, has a rounded off value of 3 × 10⁸ meters per second. His model of these waves accurately describes how energy, in the form of radiation, can be propagated through space as vibrating electric and magnetic fields. Thus, electromagnetic radiation was defined as the emission and transmission of energy in the form of electromagnetic waves. Now, Maxwell's idea about the wave nature of electromagnetic radiation was helpful in explaining other phenomena. However, he failed to explain other observations such as the nature of emission of radiation from hot bodies and photoelectric effect. We see that solids, when heated, emit light over a wide range of wavelengths, like this bright light from a light bulb. Now, in the latter part of 19th century, measurements showed that the amount of light energy emitted by an object at a certain temperature depends on its wavelength. This dependence cannot be adequately explained by scientists using the established laws in classical physics at that time, until Max Planck proposed that energy is radiated in a very small and discrete quantized amounts or packets rather than in a continuous unbroken wave. Planck called the packets of energy quanta, and he was able to determine that the energy of each quantum is equal to the frequency of the radiation multiplied by a universal constant that he derived, now known as Planck's constant or h, which measures the energy of an individual quantum and has a value of 6.63 × 10⁻⁴ joule-second. Furthermore, energy can be gained or lost only in integral multiples of a quantum. 5 years after Planck presented his quantum theory, Albert Einstein used this theory to solve another phenomenon, which is the photoelectric effect. It is a phenomenon defined as the ejection of electrons when light or other forms of electromagnetic radiation strikes a material. It was observed that only certain frequencies of light are able to cause the ejection of electrons, and it could not be explained by the wave theory of light. So Einstein proposed that rather than visualizing beam of light, it should be viewed as a stream of particles of electromagnetic energy, and these particles of light, which are now called as photons, held energy. Thus, it can be understood that different frequencies of light carry photons of varying energies. So, for the photoelectric effect to occur, the frequency of the photons should equal the amount of the energy that binds the electrons in the metal, so that the light will just have enough energy to knock the electrons loose. If light of a higher frequency will be used, electrons also acquire some kinetic energy aside from being ejected from the material. As a summary, the more intense the light, the greater the number of electrons emitted by the target metal. The higher the frequency of the light, the greater the kinetic energy of the ejected electrons.
Hi, I'm Raymond James Adame and I'll be reporting about Bohr's theory of the hydrogen atom and the dual nature of the hydrogen atom. First, the Bohr's model of hydrogen, which is based on the planetary model, in which the electrons revolve around the positively charged nucleus, like the rings of Saturn or how planets orbit the sun around the solar system. Next is the quantization of electronic structure. Building from the planetary model, Niels Bohr added an assumption about the electrons being quantized. He suggested that electrons can only orbit in rings or shells with a fixed radius, and only shells that fit in the equation below are allowed. R times n is equal to n squared times r times 1, where n is a positive integer. R times 1 is the Bohr radius, which is the smallest allowed radius for hydrogen, and Bohr discovered that R times 1 has the value of 0.529 times 10 raised to negative 10 meters. And while keeping the electrons in a circular, quantized orbit around the positively charged nucleus, Bohr was able to calculate the energy of the electron at the nth level of hydrogen, which is E times 1 is equal to negative 13.6 electrovolts. Using the equation, E times n is equal to negative 1 over n squared times 13.6 electrovolts. E times 1 is the lowest energy or ground state energy of a hydrogen electron. And now Bohr was able to describe the process of absorption and emission in the electron structure. His model states that an electron will absorb energy in the form of photons to get excited to get to a higher energy level as long as the photon's energy was equal to the energy difference between the initial and final energy levels. And upon jumping to a higher level or excited state, the excited electron will release a photon to relax and go to a lower and stable energy level. And the energy levels and transition can be illustrated using the energy level diagram. Here, we have an electron relaxing back to the second energy level of hydrogen. And the emitted photon's energy level is equal to the difference between the two energy levels for a transition. With the equation below, delta E is equal to 1 over n times low squared minus 1 over n high squared times 13.6 electrovolts. And you can also solve for the relationship between the energy and frequency using Planck's constant h, where V is equal to 1 over n low squared minus 1 over n high squared times 13.6 electrovolts over h. Finally, we can also solve for its wavelength using the relationship between the speed of light c, frequency v, and wavelength lambda. 1 over lambda is equal to 1 over n times low squared minus 1 over high squared times 13.6 electrovolt over Hc.
So after discussing what Bohr's theory of hydrogen atoms and its dual nature, we will be moving on to the concept of quantum numbers in quantum mechanics. So when we are talking about quantum, a lot are probably intimidated by the word quantum itself, but it only actually means small, discrete unit of a certain phenomenon. For instance, a quantum of electricity is an electron. Same goes with the quantum of light, which is a photon. So moving on to quantum mechanics is the science of dealing with matter and light on a subatomic and atomic scales, along with their behavior in space. It is also a set of mathematical rules where the roots of physical theories are formulated. This is an important tool in general science that is extra useful and is best understood at a theoretical level. to study and discover the electric structure of chemical compounds and their mechanisms, thermodynamics and kinetics of chemical reactions. In comparison with classical mechanics, these happens at a specified place at a specified time. For example, the collisions. Collisions can only exist in a certain period at a certain time. Same goes with force and the other concepts of physics, general physics. It is a complete opposite to quantum, where objects exist in numerous probabilities. Like, for example, certain object A could either exist on point A or at point B, but there is no certain that we will find out where that certain object will land on. So under quantum mechanics is the quantum numbers. We have four. First of all is the principal quantum number. This designates the energy level of or the principal electron shell, denoted by n, since n depicts the most probable distance of electrons from a nucleus. It is always a positive integer that starts with number 1. There's no such thing exists as n is equal to -2, -3 as principal quantum numbers. For example, n is equal to 4 rather. It means it describes the fourth principal shell. Next quantum number is the angular momentum quantum number. This describes the shape of the orbital. It could either be a sphere, a dumbbell, or the SPDF ones. This plus their angular distribution. This is denoted by L, since each value of L depicts the specified S, P, D, F subshells, which makes them unique in their own ways. This is also dependent on our principal quantum number. It could be any positive integers, but it cannot be larger than n. Or in short, n minus 1. So for example, if your n is equal to 4, then the possible angular momentum numbers are 0, 1, 2, or 3. So the third quantum number is the magnetic quantum number. This determines the number of orbitals along with their orientation within a subshell, denoted by m sub l. Apologies if I could not make L subscript here. Anyway, this is heavily dependent on the value of angular momentum quantum number L. Values could range from a negative number to 0 to a positive integer. So, example, if m is equal to 3 and L is equal to 2, then the possible m sub L values are -2, -1, 0, 1, or 2. Next is the electron spin quantum number. This last quantum number describes the direction of the electron spin and also a determination if the atom has the ability for the generation of magnetic fields or not. It is denoted by m sub s and only has a fixed value of either 1/2, an upward spin, figured by an arrow pointing up, or -1/2, a downward spin, or an arrow pointing down. As these set of rules determine the measures of an atom, there are also restrictions to it. First is the Heisenberg uncertainty principle. According to this principle, there is no precise measure regarding the exact position and momentum of electrons at the same time. So this is why no decimal numbers such as 1.7, 2.2, 3.4 exist in principal quantum numbers. Also, there are no partial waves exist. Next is the off-Gauss principle. It is a must that the lower energy level scales should be occupied first with both upward and downward spins before filling out the higher energy ones. We cannot start right away filling up, let's say, n is equal to 4 or the fourth principal shell, or we start at the first energy level, jump to the second energy level, and skip the third one to go to the fourth energy level right away. Next is the Pauli exclusion principle. It simply states that no two electrons in the same atom can obtain identical values for all of their designated quantum number. Even if the first quantum numbers all have the same value, let's say n is equal to 3, L is equal to 2, m sub L is equal to -1. What makes them unique is the spin number. only one half or an upward spin can exist and only one downward can exist, given the first three identical quantum numbers. Last is the Hund's rule. This states that every orbital in a certain subshell is supposedly and singly occupied with one electron before any other orbitals could be paired or doubly occupied. It is also required that all electrons that contain one electron is of the same spin. So that is all for quantum mechanics and quantum numbers. Thank you so much for listening.
Let's now proceed to the fourth subtopic, which is the atomic orbitals and electron configuration. In the first slide, we are going to differentiate an orbital from node. An orbital is a region in space where there is a high probability of finding an electron. If you're going to take a look at the first figure, you can see that there are different types of orbitals. And on the other hand, we have the node. A node is a region in space where there is no or zero probability of finding an electron. There are actually two types of nodes. First is the angular node, second is a radial node. So according to Heisenberg uncertainty principle, it's just not possible for us to locate with certainty where an electron is and where it's going to be an instant later. So suppose you have a hydrogen atom, a single hydrogen atom, and we all know that it only has one electron. And you've wanted to plot the probable location or position of this electron, and you've done it. Soon afterwards, you've found out that it is in its new position, and you have no any idea at all how it got there from its previous position to the current one. But you kept on doing this over and over again, and until you found yourself building up a sort of a 3D map of the places that the electron is likely to be found. I would like you to look at the first figure, which is the 1s. I think what we can interpret here is that Heisenberg uncertainty principle as well as the Schrodinger equation really contributed a lot when it comes to um, elucidating how we came to know what we know regarding the shapes of these orbitals, like how an s orbital would assume a spherical shape, how a p orbital would assume a dumbbell shape. Okay, what else can we deduce from here is that each orbital has a name. Let's say, for example, you have 1s, you have 2s, 2p, 3s, 3p, etc. SPDF indicate the shape of the orbital, just like what I've mentioned. An s would assume a spherical shape, and p orbital would have a dumbbell shape, and a d orbital would have a four-leaf clover shape, etc. Since we know that we have only one s orbital, so there are two maximum electrons that can be carried by an s orbital. And since we have three p orbital, we have six maximum electrons. We have five d orbitals, so we have a maximum of 10 electrons, and seven f orbital with a maximum of 14 electrons. Atomic orbital diagram is a visual representation of electrons in an atom. Here we have fluorine atom in its ground state, and we have 9 electrons in a fluorine atom. An atomic orbital diagram is designed from lowest energy level to the highest energy level. And the higher the energy level is, the higher the potential energy, and the further away from the nucleus. We can see here that the 1s orbital is the closest orbital to the nucleus. And constructing an orbital diagram, we need to follow different principles and rules. First thing we need to follow is the off-bow principle. It states that we need to fill in electrons from lowest energy level going to the highest energy level. So in this case, the 1s first. And the second thing we need to follow is the Pauli exclusion principle, wherein it states that um, there are only maximum of two electrons allowed for each of the orbitals, and the electrons must have an opposite spin. So one electron is oriented upwards, and the other electron is going to be oriented downwards. So that's the same manner will be applied for 2s orbital. And for Hund's rule, it is exclusive for degenerate orbitals. When we say degenerate orbitals, these are orbitals which have the same energies. So for these orbitals, we need to put one electron in each of the orbitals and before we pair them up. So The convention, this is just for convention, the 2px, 2py, and 2pz. It is not in any particular order. So you can put 2pz first, and then 2px, and then 2py. It's not going to affect anything because these are degenerate orbitals. So what else we can depict here is the electron configuration of the fluorine. So we just need to find the we just need to identify how many electrons are inhabiting a certain orbital. So let's say, for example, we have in 1s 2 electrons. In 2s, there are 2 electrons, and in 2p we have 5 electrons. So the electron configuration for fluorine will be 1s2, 2s2, 2p5. Last one is the paramagnetism and diamagnetism of an atom or material. If it's paramagnetic, at least one of the electrons are unpaired, and it is um, attracted to a magnetic field. And if it's diamagnetic, all of the electrons are paired and it's not attracted to a magnetic field. In this case, fluorine atom is a paramagnetic atom. You don't need to construct an atomic orbital to be able to know the electron configuration of a specific atom. Some of us use mnemonic devices, just like what you're seeing on the left side of your screen. It's easy to use. You just have to follow the orientation of the arrow. And some of us could also use a periodic table. If we're given a periodic table, you just have to locate where is the S block, the P block, D block, and the F block. So in this case, I have color assignment for each of the blocks. So for the S block, it's yellow. For the P block, it's red. For the D block, it's green. For the F block, it's blue. So let's say we are asked to find or to write the electron configuration for arsenic. We know that it's in the P block. So we need to follow the pattern from left to right and top to bottom. So first in the H, for hydrogen and helium, that's 1s2, followed by 2s2, lithium beryllium, 2p6, boron to neon, and 3s2, sodium magnesium, 3p6 aluminum to argon, 4s2 potassium to and calcium, and 3d10 scandium to zinc, and 4p3 gallium to arsenic. So that is the electron configuration for arsenic. And we also use shorthand electron configuration. How is this working? You just have to have a reference point. And in this case, the reference point is a noble gas from the previous period. So for arsenic, the previous period is the third period, and the noble gas there is argon. So you need to enclose with square bracket you need to enclose argon with square bracket, followed by the following orbitals. So you have 4s2, 3d10, and 4p3. The only thing that you need to do here is to arrange the energy levels in an ascending manner. So first is 3d10, 4s2, and 4p3. So that is the shorthand electron configuration for arsenic. An angular node or a planar node is either x, y, and z planes where electrons are not present, and it has a formula of An is equal to L, where L could be 0, 1, 2, or 3. A radial node is a spherical surface region where there is a zero probability of finding an electron, and it has a formula of Rn equal to n minus L minus 1. So in this figure, you can see that you can easily identify the radial node because it is a spherical surface region. And the angular node is the plane which is seemingly bisecting this orbital. This is, by the way, a 3p orbital which has one angular node and one radial node. So we're going to calculate for the angular node the number of radial node as well as the total node. The technique that I'm using is to find first total node and then angular node, and then I'm going to find the radial node by subtracting angular node to the total node. So in this example, it's 5p. Total node is n minus 1, so 5 minus 1 is 4, and p has a corresponding value of 1. So I'm just going to get the difference. 4 minus 1 is equal to 3. That's the radial node. For 6s, 6 minus 1 is 5. S is equal to 0, so 5 minus 0 is 5. For 7f, 7 minus 1 is 6, and the f is equal to 3, so 6 minus 3 is 3. For your exercise, please answer the following questions.
Good day, guys. I am Jennelyn Laquinta from Chem 41, and for this segment of our discussion, we are going to talk about the building up principle. I know that we have already encountered the term Aufbau principle, which is, by the way, a German word for building up. But for now, let us relate this term to electronic configuration and the formation of the periodic table. This principle dictates that as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the atomic orbitals. This means that the arrangement of electron configuration is in a diagonal path, just like in the figure shown in the slide. Now, we know that as we go further to the periodic table, the electronic configuration will also lengthen. If you notice from your own periodic table, there are shorthand style of writing the electronic configuration, and that is by the noble gas core, wherein it shows in brackets the noble gas element that is most nearly precedes the element in interest. To expound this idea, let us answer the following problem. What is the shorthand form of electronic configuration of potassium with atomic number 19? Now, listed here is the complete electronic configuration of potassium. Obviously, we cannot include this much information in our periodic table. So another way of writing this is by providing the preceding noble gas, which is argon, to the element potassium and enclosing it with a bracket. Following that are the remaining configuration, which is 4s1. Note that this does not only shorten the electronic configuration but also helps us remember and understand that the remaining configuration is intended for the valence electron of ground state potassium. On the other hand, the electrons represented by the argon core are the core electrons of potassium. Moving forward, we are going to relate the electronic configuration to the arrangement of elements in the periodic table. As you can see, the yellow part or S block is intended to electrons that share or elements that share distinct characteristics with each other, and that their valence electrons are situated in the s orbitals. The same goes for p, d, and f block elements. Now, let's focus on some elements that have a distinct black borderline, like chromium. These elements are examples of anomalies to the pattern given by the Aufbau principle. To elaborate this, let us answer this problem. Do you ever wonder why chromium have an electron configuration ending with 4s1 3d5 and not 4s2 3d4? This has something to do with the concept of stability brought by half-filled and fully filled orbital. To answer the question, this inconsistency to the rule arises with the enhanced stability brought by the half-filled 3d orbital. This also applies to copper with an electron configuration ending with 4s1 3d10. This means that half-filled and completely filled 3d orbitals have greater stability than a fully filled 4s orbitals. This inconsistency is also observable for silver and gold electronic configuration. Now, to test your understanding, please take time to answer this question in the comment section. Explain why lanthanum have an electron configuration ending with 6s25d1 instead of 6s24f1. This is another irregularity in the pattern because instead of the last electron situated in 4f orbital, like the one suggested in the Aufbau principle, the last electron of lanthanum is located in the 5d orbital. Hint: this has something to do with the distance of orbitals involved. As a summary for our group's discussion, we have acquired a list of important formulas that will help us solve problems relating to the quantum theory. On the other side are the corresponding values of constants and the designation of each letters or values. We can use this and derive another formula depending on the given values and the missing value. Take note that it is important that we recognize the nature of the problem or the topic where the problem fits to shorten our solving time. Another guide that we have formulated is all about the quantum numbers. We know that in answering questions relating to this might also be time-consuming. So let me explain this figure. The first line in yellow represents the principal quantum number or energy level, which can be in values of 1, 2, 3, and so forth. The second line in green represents the orbitals, which are s, p, d, and f, and the corresponding angular momentum quantum number denoted by L values. By 0 L value, we must automatically associate it with s orbital. The same goes for L values of 1 for p, 2 for d, and 3 for f. The third line in blue denotes the magnetic quantum number m sub L. For each orbital, there are corresponding m sub L values. For instance, if the given L value is 1, we should automatically expect m sub L values of -1, 0, and +1 only. If the m sub value given is 2, we should eliminate that from our choices of correct configuration. For the last line, in orange, is the spin quantum number. We know that there are only two values for this, which is positive 1/2 and negative 1/2. Otherwise, it is incorrect. Under that are the maximum number of electrons per orbitals. We can also use this to recheck the correctness of a particular set of quantum numbers. That is all for the Quantumverse discussion of term Erbrium. These are the references we've used for this report. Next is the members of Team Erbrium. And finally, thank you for listening.